8.1 Formulas for sequences. Well, what is a sequence? A sequence, by the definition in the book, is a function whose domain is a set of consecutive integers greater than or equal to k, which many of you don't understand. The basic idea of a sequence is a list of numbers. So, for instance, 3, 5, 7, 9, that's a list of numbers. We can talk about this one being the first term, this one being the second term, this one being the third term, fourth term, and so on. So in other words, the term is the order that it goes in. The value is the actual number in the sequence. Well, and so up in your definition, see how it says the domain is a set of consecutive integers? Well, these numbers right here, first, second, third, fourth, those are the consecutive integers. So I guess you could really kind of liken it to the fact that the terms represent the x values, and the value of the term in the sequence would represent the y values. So in essence, what you're dealing with is a function. Now, it's not a continuous function like what you're used to dealing with. It's a discrete function, meaning that there's lots of space in between each of the points. First term is 3, second term is 5, third term is 7, fourth term is 9. But you cannot connect the dots on the graph because they do not connect. There's nothing in between them. All right, now at the beginning of our textbook section, there is a rectangular sequence. Those are called figurative numbers, and it's kind of a complicated example, so we're not going to go through that example. I'd really like to stick with two different types for now, called the arithmetic and the geometric, which you learned about last year. So this should be more or less a refresher course for you. The arithmetic sequences, here's an example, 3, 5, 7, 9. We started out with that example before, so let's just take a look at this one. There is a constant difference between each of the terms. That constant difference, we will label it D, and you can find that constant difference by taking any term and subtracting the previous term. So you pick a term and subtract the previous one. Or pick a term, subtract the previous one. Pick a term, subtract the previous one. And all of them should come out to the same number. That, in this case, is the constant difference between the terms. Now, there are two types of formulas. And yes, there will be a formula sheet which will have these formulas on it. So don't panic and come to class, as I know a few of you will, and say to me, oh, do we have to have these memorized? Yes, I know, it sounded just like him, didn't it, Rosman? So, here are the formulas. There's an explicit one. Don't go where I think you're going with that. And then there's the recursive one. The recursive one is sometimes the only pattern that we have. But it is not my favorite pattern because it always depends on knowing the previous term. So, if you don't know the previous term, you're really stuck. That's why the recursive pattern has a starting value, and it tells you what to do to find the next term. And we'll go through that here in a minute. In fact, I'll do that right now. It says that the next term is equal to the previous term plus the constant difference D. Now, take a look at those subscripts. N is a subscript, not an exponent. N minus 1 is a subscript, not an exponent. So, when you use the letter N, that's what I'm saying is the next term, and N minus 1 would be before that. For instance, if you were looking at a list of numbers and you came across a sub n, the one after it would be a sub n plus 1, and the one before it would be a sub n minus 1. I know that's kind of confusing notation, but you can kind of get the idea of place in the sequence. Let me back out so you can see. Whoops, too far. The explicit formula looks like this. It says that the next term in the sequence can be found by taking the first term plus the constant difference times n minus 1. Now this one doesn't rely on any previous terms, so guess what? This is my favorite one because you can go straight to any term in the sequence. If you want to know the 500th term, use this formula because you'll go straight there by plugging in 500 in for n. This one over here would be a bear because if I wanted to know the 500th term, I'd have to know the 499th term, and the 498th term, and the 497th term, and all the way back to the first term. So this would not be my favorite choice if you wanted to know the 500th term. I would much prefer, rather, dealing with an explicit formula. Obviously, you can see that this explicit formula looks a lot like a slightly modified version of the point-slope form of the equation of a line. That's because the arithmetic sequence is linear. Yes. So we're dealing with a linear function with the arithmetic sequences and their patterns. We might be dealing with problems that say things like write the first 4 terms, and then we were given a recursive pattern. Also, I can clearly see that the first number in my sequence is a 2. Don't ignore the first term of the sequence. Make sure you use the first term of the sequence. Then I need to follow the pattern. The pattern says to find the next term, we take the previous term and add 5. So all I'm going to do is I'm going to add 5. To find the next term, you add the previous term plus 5. To find the next term, and so all you're doing is adding 5 each time to find the next one. Not very difficult to follow a recursive pattern. It would be challenging to find the 500th term because I don't want to waste a bunch of time finding 499 terms before it. Well, in the next one, if I'm going to find terms, if I want to find the first term, I plug in a 1. And if I want to find the second term, I plug in a 2. So what do we got there? 1 times negative 3 is negative 3. So find the third term, plug in a 3. So what do we have there now? 2 times 3 is negative 6, plus 6 is 0. And the fourth term, plug in a 4. So those are the first 4 terms of that particular sequence. 6, 3, 0, negative 3. Oops. Okay, example 3 in the book's kind of interesting. I like that one. What position or term does 127 have in the arithmetic sequence below? We start with 16, 19, 22. Clearly, we can indicate or see that the constant difference between terms is positive 3. It's going up by 3, but we don't know which term this one is. So we know that the first term is 16. We know that the constant difference is 3. We don't know what term is 127. So we'll call that a sub n. So if we have the formula a sub n equals a sub 1 plus d times n minus 1, what do you think we're solving for? Of course we're solving for n. So obviously we're going to subtract 16 to the other side, so we have 111 equals 3 times n minus 1. We're going to divide by 3. What do we got there? 4, 1, no, what is, wait a sec, is that 37? Yep. So now we have 37 equals n minus 1. is 38. We're talking about the 38th term of the sequence. Now, the other type of sequence that we dealt with last year was called the geometric sequence. Okay? So, it's a ratio of consecutive terms, and that ratio is constant. Instead of being a difference, it's a ratio. Yes, that means we're dividing. So, any term divided by its previous term has to come up with the same number. So for the ratio, or the sequence 2, 6, 18, 54, if I take any term and divide by its previous term, whether it's 6 over 2, or 18 over 6, or 54 over 18, every time I come up with the number 3, that's my multiplier. And likewise, we have explicit formulas and recursive formulas. Obviously, the recursive formula has to have a starting point, and it says that the next term is equal to r times the previous term. That's what that g subscript n minus 1 means, previous term. The explicit variety looks like g sub n equals the first term times r to the n minus 1 power, which looks an awful lot like the exponential model because this model is exponential. So just like the arithmetic sequence went with the linear model, the geometric sequence based on multiplication obviously goes with the exponential model. So for instance, a car depreciates 25% per year, and the original cost is $25,320. Find the value at the beginning of the second year. So we have the value at the beginning of the first year is $25,320. We're looking for the value for the second year. Now, I'm going to use the multiplier, right, to the n minus 1 power. In this case, it would be 2 minus 1. What's the rate? If you're depreciating 25%, you are keeping 75%. Oh, remember that whole thing last year? B equals 1 plus R, where R is the growth rate. Not to be confused with the ratio in this case, all right? Which I know can be terribly confusing, but our ratio is 75%, our multiplier that we're using. Whereas from this problem, I realize that I am losing 25%. So that's an unfortunate use of the same letter. They do mean something different. This B value matches that value right there. So that would be more appropriate. But you will see in the book that they use R for ratio. So you might want to just get used to that. Write the explicit formula. Well, we kind of used the explicit formula in the last question. So g sub n is equal to g sub 1 times r to the n minus 1. In this particular case, g sub n equals 25,320 times 0.75 to the n minus 1 power. That's really what they were looking for in this particular question. And lastly, in how many years will the car be worth $1,000? So we've been given $1,000. Maybe I should say, in how many years will the car be worth $1,000 or less? It may not be $1,000 right on the nose, so, but we are going to set it up 25,320 times 0.75 to the n minus 1 power. Okay, if you're thinking about this logically, you should see that the first thing we need to do is divide out the 25,320. And if we take 1,000 and divide out the 25,320, we ended up with 0.0395. So 0.0395 equals, or is approximately equal to, 0.75 to the n minus 1. Okay? Yes, you should be thinking about logarithms because we need them. The base is 0.75, the argument 0.0395, and it is approximately equal to n minus 1. using your powers of logarithms, you know that you can take the log of the argument over the log of the old base, and we're changing it to base 10 so our calculator can handle the calculations. So we have log 0.0395 end parenthesis, make sure you use the end parenthesis, divided by log 0.75 end parenthesis equals 11.23. So n minus 1 is approximately equal to 11.23. And if we add 1, we get an n value of 12.23. Now, so the 12th term would not create a value of under $1,000 or 1,000 or less. So we have to actually go to the 13th year. The beginning of the 13th year would create that value of $1,000 or less. See you in class.